let us study the orthogonal basis and Gram-Schmidt process. There are two conditions for a vector to be called as orthonormal. A set of vector we call it as orthonormal when every vector in the set has a magnitude of unity, and also all these vectors should be mutually orthogonal to each other. And in order to get its magnitude, we have to calculate its length first, and we have to divide the vector by the length in order to make it a unit vector. Two vectors are said to be orthogonal if their dot products are 0. Suppose if I have two vectors q1 and q2, q1 dot q2 or q1 transpose q2 should be always equal to 0. And the second condition is each of the vectors should have a magnitude that is equal to 1. That we call it as unit vector. And in general, I can say that the vectors q1, q2 up to qn are orthonormal if qi transpose qj is equal to 0 whenever I is not equal to j. Means it is orthogonal. It is as good as saying qi dot qj equal to 0, which means when it is 0, we call it as qi is orthogonal to qj. Second condition is qi transpose qj or qi dot qj has to be 1 if I equal to j and giving normalization. Usually we call a matrix with orthonormal columns as Q, and Q, if I define it for 3 by 3 matrix, and it says that Q12, Q13, Q21, Q23, Q31, Q32 all has to be 0 in this matrix, and this vector, if it has to be unit vector, Q11, Q21, Q31, if this vector set should be unit vector, then Q11 should be 1. Similarly, Q22 should be 1, Q33 should be 1. Let us take an example to understand the orthonormal vectors. We consider three vector sets. V1 is equal to 1, 0, minus 1. V2 equal to 1, root 2, 1. V3 equal to 1 minus root 2, 1. First, let us check its orthogonality. That is, V1 has to be orthogonal to V2, V2 has to be orthogonal to V3, and V3 has to be orthogonal to V1. That can be done by getting their dot product. So V1 dot V2 will be equal to, it is V1 transpose into V2. V1 transpose is 1, 0, minus 1, and V2 is 1, root 2, 1. When I calculate it, I get the value as 0, which means that V1 vector is orthogonal to V2 vector. Second one, V2 dot V3, that is V2 transpose multiplied by V3. V2 transpose is 1 root 2 1 multiplied by 1 minus root 2 1. I am going to get the resultant as 0. This means V2 is orthogonal to V3. Now the last condition, V3 dot V1, I have to take the transpose of V3, that is 1 minus root 2 1. It is multiplied by V1, we will get it as 0, which means that V3 is orthogonal to V1. So I can write that all these three vectors V1, V2 and V3 are orthogonal. So the first condition for orthonormal condition is satisfied. Second condition is we have to prove that all these vectors V1, V2, V3, we have to make it as orthonormal by making them unit vectors. That can be done by dividing by the length of the vector. Let us say U1 is equal to V1 divided by length of V1. So that gives you 1 divided by root 2, and it is 1 0 minus 1. So resultant is going to be 1 by root 2 0 minus 1 by root 2. If I calculate the length of U1, I am going to get the answer as 1. It turns out to be unit vector. Let us say that U2. U2 is given by V2 divided by length of V2, that is 1 divided by root of 1 square, root 2 whole square, that is 2 plus 1 square, and multiplied by V2, 1 root 2 1. We are going to get the resultant vector set as 1 by 2, 1 by root 2, 1 by 2. If I want to compute the magnitude or the length of U2, I am going to compute here. It will give me the answer as 1. It turns out to be unit vector. And U3 is equal to V3 divided by length of V3, that is 1 divided by root of 4 multiplied by 1 minus root 2 1, that is equal to half minus 1 by root 2 half. So you can compute the length as root of half square plus 1 by root 2 whole square plus half square, that will give us 1. So therefore we can say that U1, U2, U3 are orthonormal vectors, and having all these three vectors will be orthogonal to each other, because V1, V2, V3 we have proved that they are orthogonal to each other. Both the conditions for orthonormality are satisfied, so we can say that U1, U2, U3 are orthonormal vectors. Let us study the characteristics of orthogonal matrix. Let us consider a matrix Q, orthogonal matrix, which will be having orthonormal columns. Orthonormal columns means it is the diagonal element will be equal to 1. Then we know that Q transpose Q is equal to I, which is the identity matrix. Second characteristic is an orthogonal matrix is a square matrix with orthonormal columns. That means in that case your Q transpose is always equal to Q inverse. We'll take two examples to understand these two characteristics. First one is Q is equal to cos theta minus sin theta cos theta. When we take a inverse of Q, we get Q inverse, that is same as Q transpose, that is cos theta sin theta minus sin theta cos theta. We'll take a second problem where you can see that the diagonal elements, if I rearrange this, these are the three elements which form the diagonal elements of the matrix, and you can see that it has a value 1. P inverse is as good as saying P transpose, that is equal to 0 0 1 1 0 0 0 1 0. So these are the characteristics of orthogonal matrices, and this property is exploited in many engineering subjects. Third characteristic is multiplication by any vector x to q, that is the orthogonal matrix, then the length will not change. Length will remain unchanged. That means length of q into x is equal to length of x for every vector x. And the fourth characteristic is if the columns in a matrix are orthonormal to each other, then we can also say that rows of that particular matrix will also be orthonormal to each other. If there are orthonormal columns, then we can say that there will be orthonormal rows. Gram-Schmidt process helps us to convert the vectors which are not orthonormal to each other into vectors those are orthonormal to each other. So let us consider three independent vectors A, B, C. We convert these three vectors into orthonormal vectors Q1, Q2, Q3. So we have several steps. The first step, we consider any of these vectors A, B, C, and we try to convert those vectors into unit vector so that we can get Q1. So I have considered the vector A and I convert this vector A into a unit vector by dividing the A by length of A. So Q1 turns out to be a unit vector. Second step, we need to compute Q2 such that this Q2 vector is orthogonal to vector Q1. So we need to find a component B here, the second vector, which is given by B minus Q1 transpose B into Q1. From B, we can compute Q2 by dividing by its length. So B divided by length of B will give me Q2. Graphically, I can show the operation of step 1 and step 2 like this. I have a vector A. I divide this vector A by its length. I am going to get a vector Q1. Now I need to get Q2, which is perpendicular to Q1. Now first I need to calculate a component B such a way that it is orthogonal to Q1. And once I compute this B with the help of this vector B, then I have to divide B by its length in order to get the vector Q2. And we can see that Q2 is orthogonal to Q1. Step number 3 involves the computation of third orthogonal vector C from C. We know that this component C will not be in the plane of Q1 and Q2. Therefore, we have to get this C, which is orthogonal to both Q1 and Q2. That can be done by computing C equal to C minus Q1 transpose C Q1 minus Q2 transpose C Q2. And it can be converted into unit vector by dividing C by its length C. So Q3 is equal to C divided by its length C. We try to understand Gram-Schmidt process with the help of an example. We have been given three independent vectors. A is equal to 1, 0, 1, B is equal to 1, 0, 0, C equals to 1, 0. First, let us check whether these three vectors are orthogonal to each other or not. And that can be done by dot product A dot B. This term should be equal to 0 if A and B are said to be orthogonal. Now when we do A dot B, we get 1 into 1, 1 plus 0 into 0, 0 plus 0 into 1, 0. So I get A dot B is equal to 1, which means that A and B vectors are not orthogonal to each other. So we need to convert this into orthonormal basis by Gram-Schmidt process. First step is we need to find out Q1. I can choose any of these vectors. I have chosen A here. A divided by length of A will give me Q1. So therefore, I have A here 1, 0, 1 divided by the length. Length is given by square root of 1 square plus 1 square, that is root 2. So I get the resultant vector as 1 by root 2, 0, 1 by root 2. Second step is to compute the value Q2. In order to compute this Q2, I need to calculate B. is given by B minus Q1 transpose B into Q1. I have written B here minus, it is Q1 transpose multiplied by B multiplied by Q1. The resultant vector is going to be half 0 minus half. From this, I need to compute Q2. Q2 is given by B divided by its length, and that is its length is given by 1 divided by square root of length is half square plus half square. So I get this as root of half multiplied by the vector B. So I get the resultant vector as 1 divided by root 2, 0 minus 1 divided by root 3. Next step is to find Q3. In order to find Q3, which is orthogonal to Q2 and Q1, we need to find the component vector C. C is given by C minus Q1 transpose C, Q1 minus Q2 transpose C, Q2. When I substitute the value of C, that is 210 minus, it is Q1 transpose into C into Q1 minus, this is Q2 transpose, this is C multiplied by Q2. That will give me the resultant vector as 0, 1, 0. Once I know the component C, I can get Q3 by dividing C by its length. When I divide it by its length, I am going to get this as 0, 1, 0. So now I have got 3 orthonormal bases, Q1, Q2, Q3. When I put it in the form of a matrix, I am going to get the Q. That is 1 by root 2, 0, 1 by root 2, 1 by root 2, 0, minus 1 by root 2, 0, 1, 0.
In this problem, we need to find the distance from the point Y to a subspace V. The point Y is given as 0, 0, 0, 1, and the subspace has the basis vectors x1 is equal to 1 minus 1, 1 minus 1, x2 is equal to 1, 1, 3 minus 1, and x3 is equal to minus 3, 7, 1, 3. W1 is computed as x1. It is equal to 1 minus 1, 1 minus 1. W2 is given by x2 minus x2 dot W1, W1 dot W1 multiplied by the vector W1, that is given by x2 is 1, 1, 3 minus 1 minus x2 is 1, 1, 3 minus 1. W1 is given by 1 minus 1, 1 minus 1 divided by 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1. It is multiplied by W1, 1 minus 1, 1 minus 1. So we get this as 1, 1, 3 minus 1 minus, it is 1 minus 1 plus 3 plus 1 divided by 1 plus 1 plus 1 plus 1, 1 minus 1, 1 minus 1. So we have this as 1, 1, 3 minus 1 minus 1 minus 1, 1 minus 1, that is equal to 0, 2, 2, 0. This is W2. So we need to compute W3. W3 is given by x3 minus x3 dot W1, W1 dot W1, W1 minus x3 dot w2 w2 dot w2 multiply by w2. So we substitute the values. We have minus 3 7 1 3 minus x3 is given by minus 3 7 1 3. It is dot product with 1 minus 1 1 minus 1 divided by 1 minus 1 1 minus 1 dot product 1 minus 1 1 minus 1 multiplied by 1 minus 1 1 minus 1 minus it is x3 minus 3 7 1 3 and w2 is given by 0 2 2 0 divided by 0 2 2 0 dot 0 2 2 0 multiplied by 0 2 2 0. So this will give you the answer. When you simplify this, you will get the answer as it is 0 0 0 0 0. Finally, we need to find the distance y from the subspace. So therefore, we can compute this distance. Let me call that distance as W4 is equal to, it is y minus y into v1, v1 dot v1, w1 multiply by w1 minus y into w2, w2 dot w2 to w2. w3 need not consider because it turns out to be a 0 vector. So here y value is given as 0 0 0 1 minus y is 0 0 0 0 1 1 minus 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 1 multiplied by 1 minus 1 1 minus 1 minus 0 0 0 1, it is 0 2 2 0 divided by 0 2 2 0 multiplied by 0 2 2 0, it is 0 2 2 0. So this is equal to 1 by 4 minus 1 by 4 1 by 4 minus 3 by 4. So if you find the length of this W4, you will get the distance, that is 1 by 16, 1 by 16, 1 by 16, 9 by 16. So we get this as root of 12 by 16, that gives you 3 by 4. This is the distance.
Video, we will move on to module number 5.